Okay, so we saw the quantum Fourier transform circuit, right? And we saw how that scales only polynomially with the size of the input on which you want to do the Fourier transform. And I said that the route to factoring is to do Fourier transform, then do phase estimation and order finding. So this is what we're going to discuss today. We already started discussing this last time. So the problem of phase estimation is the following. You're given a unitary U with some eigenstate ket U, right? Such that the associated eigenvalue, as you know, is pure phase, and we will write it as e to the 2 pi I phi ket U, right? And the problem is to estimate phi given the unitary U and the specific eigenstate ket U, because the phi is associated actually with that eigenstate. Actually, there should be a phi sub U to indicate that it is associated with that eigenstate, right? And of course, phi is some real number between 0 and 1, right? And what I indicated last time is that the inverse Fourier transform is going to help us to do phase estimation efficiently. So let's first look at the circuit for phase estimation, and then we will see why it works. So the key ingredient, okay, so let's first say that we want to estimate phi up to t bits of accuracy, right? What does that mean? Now phi is some real number between 0 and 1. So let's write it in this fractional binary notation, right? So we'll write this as 0.51, phi 2, phi 3, etc., phi t, right? So this, if you write this, expand this in powers of 2, you know that this is of the form, we already saw this when we did Fourier transform, right? So this is of the form phi 1 by 2 plus phi 2 by 2 squared, etc., phi t by 2 to t. So note that all your phi are binary valued variables, right? They're either 0 or 1. So this is a fractional expansion of phi in powers of 2, binary fraction, just like how we did in the case of the Fourier transform. So this is what I mean by saying I want to estimate phi up to t bits of accuracy. So in that case, I will need t data qubits, right? So we start with t data qubits, and the ancilla qubits in the eigenstate, whichever eigenstate associated with this eigenvalue that you want to estimate. And how many ever qubits it takes to represent ket U, because U could be whatever dimension, capital U, right? You use that many ancilla qubits. So this resource in some sense is constrained or fixed by the size of the unitary U whose eigenvalue you want to estimate. What the algorithm requires from you is just t data qubits, where t is the number of bits to which you want to estimate this. So these are my data qubits first. And the algorithm proceeds very similarly to what we have seen so far. All these data qubits are going to be initialized to get 0, and then we are going to do a bunch of Hadamards on them. So essentially, you're doing a H tensor T, a T qubit Hadamard. And then what I showed you towards the end of class last time is you have this eigenstate U, which is prepared, right? The ancilla is in the state U. You start doing control unitary operations, and not just control U, but control powers of U, right? And you start with the last qubit, the tth qubit, and you do one control U operation. U, of course, acts on the entire ancilla set. The second last, the t minus 1 qubit, with that as control and the eigenstate U as target, you do a U squared operation, control U squared. Then with the third one from the last, you do a control UQ, not U cube, control U to the 4, okay? So powers of 2. And so on and so forth until all the way up to the first qubit. Again, this is a controlled operation. What is the power of U now?
The power t.
2 to the power t or t minus 1. The first one is 2 to the 0, right? This is 2 to the 1. This is 2 squared. So this is 2 to the t minus 1, right? So now the question is, what state are we? So what is the state of the ancilla at the end of all these controlled operations? So what we're going to see right now is that nothing happens to the ancilla. The ancilla is an eigenstate of U. It's an eigenstate of any power of U. So this is going to remain in ket U. What is going to happen is each of these controlled operations is going to add some non-trivial phase to the data qubits, to each of the data qubits. The first step, which is this n, rather t qubit Hadamard, this is just H tensor T, right? So the effect of this is to throw each data qubit into a uniform superposition of 0 and 1 with a trivial phase. So it is 0 plus 1 by root 2. Then progressively, each application of this control U is going to add some non-trivial phase to these data qubits. So let's see what non-trivial phases they add. So let's first do the first one, right? So on the tth data qubit, you have a control U. So let me write it like this. This is the control U gate. So it's a 2 qubit gate, and it acts on 0 plus 1 by root 2 tensor this eigenstate U, right? So what does this control U do when the control is, so this first qubit is a control. The control is 0, nothing. When when control is 1, it's going to act the unitary U on ket U. But the action of U on ket U is simply to pull out that e to the 2 pi I phi phase. So this is what we have. Is this step clear? So this, of course, can be viewed as simply adding this phase e to the 2 pi I phi. This is nothing but the lambda, right? This is nothing but the little lambda. This is the eigenvalue of unitary U corresponding to this eigenstate, right? So what happens to the penultimate qubit? I'll just do one more example and then the pattern will become clear to you. This is a control U squared operation. Once again, control qubit is in 0 plus 1 by root 2. Target is in the eigenstate ket U. And once again, it does nothing to the target when the control is 0. When the control is 1, this has to apply the unitary U squared on the target, right? this implied tensor product here. So then this is going to pick out lambda squared, right? Little lambda squared, the eigenvalue squared. So this is e to the 2 pi I 2 times phi. Once again, we'll pull the phase out onto the control or the data qubits, right? The ancillas back to Ketu. So this will continue like this until you can see that on the first data qubit, the action of lambda u to the t to the, 2 to the t minus 1. So it's u raised to 2 to the t minus 1. And once again, this is plus state and this is Ketu. So I hope you can see that this is going to leave the control qubit in the state. So the first one was just phi, that's 2 to the 0 times phi, 2 to the 1 times phi. So this is going to be 2 to the t minus 1 phi. This is what the data qubit will be in. And this is the answer. So we can now write down in this circuit itself what these output states are, what the states of the data qubits are going to be. So this, I'm going to omit the 1 over root 2 normalization factors. So this is going to be 0 plus e to the 2 pi I phi ket1. This is 0 plus e to the 2 pi I 2 times phi ket1, and so on and so forth. E to the 2 pi I 2 to the t minus 1 phi. That's all in the phase ket1. So let's write down what the data qubits, the t data qubits look like after the application of the sequence of control unitaries. So the complete state of the data qubits, the t data qubits, after all the lambda u raised to 2 to the I, right? So remember, the first one is in the state 2 raised to t minus 1 phi. But now I'm going to obviously do the binary expansion of phi, right? And since phi is some real between 0 and 1, this is going to be fractional powers of 2. We just saw that expansion. So this is now of the form phi 1 by 2 plus phi 2 by 2 squared, etc. So what is this going to be? What is this phase going to be? In that notation, this binary fractional notation?
It will be phi t, 0.5 t.
Yeah, exactly. Good. So this is basically going to be 0.5 t ket 1, right? Why is that? Because 2 to the t minus 1 phi is nothing but 2 to the t minus 1, phi 1 by 2, phi 2 by 2 squared, etc., phi t by 2 to the t, right? And so the only non-trivial power phase that you're going to have is the one with the phi t, right? So recall this. So this is the first data qubit. So this tensor. So now you see the sequence will emerge. So you will have 0.5 t minus 1 phi t ket 1. Okay, because the next one will have 2 to the t minus 2. So there'll be two of these bits in the binary representation of phi that will come into the phase, right? etc., all the way down to the last one, which will have all the t bits coming into play. So this will be 0.51, phi 2, etc., phi t, get 1. And of course, this whole thing with the normalization 2 to the t by 2, right? So what does this final state of the data qubit remind you of? We have written down this expansion a few times now, this kind of product form with all these fractional powers of 2 in the different phases.
QF.
Yeah, QFT on what? So remember phi 1, phi 2, etc. are all
Phi 1, phi 2, T qubit bit sequence.
correct, exactly. So this is indeed the final state of the data qubits is nothing but the action of the quantum Fourier transform on the computational basis state whose binary representation is phi 1, phi 2, phi 3, etc., phi t minus 1, phi t. And this is indeed what we called as the phase phi in some sense. So you can think of this as ket phi, but since phi is something between 0 and 1, and we call this as, in powers of 2, so let's not call it that. But the point is, if I want to estimate phi, it means that I want to know what is phi 1, whether phi 1 is 0 or 1, whether phi 2 is 0 or 1, etc., up to phi t. So what I have ended up with at the end of this circuit is the Fourier transformed state corresponding to this state. But I actually want this state, right? Because this is the state which has information about the different phi i's, about the binary representation of this phase phi. So the last step of the phase estimation procedure, or let me say the phase estimation circuit, is to perform an inverse Fourier transform. So you perform an inverse QFT on the data qubits. That will get you to this state, which is ket phi 1, ket phi 2, etc., ket phi t. And then, of course, you do a measurement. So remember, QFT is a unitary transformation. So the inverse QFT is nothing but the adjoint of this transformation. Whatever is the transformation we wrote down last time, the circuit, you'd simply have to take the adjoint of that sequence of unitary matrices, and that will be the inverse QFT, right? So let's draw the full schematic of the phase estimation procedure. So we start with T data qubits. So often these are, like I said, denoted with a single line and a backslash. The backslash is to denote that there are multiple qubits here. So let me write it like this. So this is basically 0 tensor T. That's the state. Then this is acted by a Hadamard tensor T, right? So remember that it's important that you first throw the control qubits, because these are the control qubits, these data qubits. It's important that you throw them into the superposition state. If you do not do that, you're not extracting this phase information by doing the control unitaries, right? So because you're doing the control unitary with a control state that is in the superposition, that's what extracts the phase information for you. So these are the ancillars which are in Ket-U. And after this Hadamard tensor T, I will just draw one control box and I will say that you do u raised to 2 to the j, okay, for 0 to t minus 1, right? So this is a whole sequence of control u's like this. Then at the end of it, you again have these t data qubits. The ancillas don't matter, they are just there for the ride. You have to do the inverse Fourier transform here. So that is QFT dagger. And then you do a measurement where you measure each of these qubits in the standard computational basis. So it's very simple. It's just you measure in the 0, 1 basis. Each of these T data qubits is to be measured in the 0, 1 basis. Okay. So I hope this idea is clear of phase estimation and how the Fourier transform helps you to do phase estimation. You notice that there is not much overhead over and above the Fourier transform. The main overhead actually, it turns out, is in actually implementing these lambda, these controlled u raised to 2 to the j. And it turns out that there is a way to do this by a procedure called modular exponentiation. I will not get into this, but I will refer you to chapter 5 of Nielsen Chuang for this, where they show how you can do this, or they estimate the circuit complexity of this. So this is, if you're interested, please look up box 5.2. And they put some bounds on this, and they show that this is only a polynomial scaling. Okay, that this is no worse than a polynomial scaling, polynomial in the size of this u that you want to estimate. So in terms of resources, what we need to estimate as far as phase estimation is concerned is what is this T. So again, one can put some bounds on that. One can do a bit of error analysis on the phase estimation procedure, right? Because after all, you're trying to estimate some real number between 0 and 1. So how close can you get? And what is the T that is required to get close, right? That's the question. So again, I'm not going to do this performance analysis, but I will just state the final result. I mean, I'm just referring to Nielsen Chuang since that's the notation, etc., that I follow. Okay, so suppose you want to, so now let's say we do this procedure with these T qubits, right? So we get these values, right? Phi 1, phi 2, phi 3, etc., phi T. Okay, but this may not be actually the phase phi that you wanted to estimate, but this may give you some number phi tilde, right? So the question is, how close is phi tilde to phi for a given size T? Okay, and this is the statement that suppose you want to estimate so let me say this is phi tilde, which is close to phi. Okay, so suppose you want to estimate the phase to within an error. So let me call this error as epsilon. Yeah, so this is the statement. So if you want to estimate phi, so let me say this in terms of bits only. So if you want to estimate phi to within n bit accuracy, so if you want to estimate phi accurate to n bits, with high probability. So let me say with a probability of success, which is at least 1 minus epsilon, then we need T to be of the order of n. So this is why I said when you choose T bits, you're estimating phi to an accuracy of roughly T bits, right? But this is the exact statement that what is the error. So this error goes as log of 2 plus 1 over 2 epsilon, where epsilon essentially captures the probability of failure, right? So this is some ceiling function, okay? So we need these many qubits. Okay? So the smaller you want to make this probability of failure of estimating to n bits, the closer you have to take T to n, right? And in some sense, the more number of data qubits that you use, the smaller you can make this failure probability. Okay, so this is just a statement that I wanted to show you. I'm not going to prove this statement. It requires some amount of analysis, which will probably take up the rest of this class. But instead of doing that, I would rather move on to showing you how this eventually leads to factoring. Okay. So any questions?
What exactly is the probability of failure here?
Yeah, so the probability of failure basically says that there is some see, you're only going to estimate the phi, right? So you're going to get some number which is going to, you're going to get some real number which is within some region of phi, right? And this epsilon basically captures what is that region within which you're estimating phi. So you can think of it as an error if you wish, right? You can think of this as some kind of distance estimate or an error, right?
Means even like there is some error because we are kind of truncating it to n bits, and there is an extra error epsilon which is because of means other things like is that what it is?
No, so the idea is this, that okay, so let me write this out properly maybe. So there is a measurement at the end, remember, right? And the way I have shown you, it's as if you have this exact, so I said that the this is exactly QFT on this particular bit string, right? And I said that this bit string is exactly phi, right? So I said the inverse Fourier transform exactly gives you back what I call ket phi, right? But actually what it is going to give you is some ket phi tilde, right? And so there is probably some, you can think of some region of some set of strings around this binary string that your measurement is likely to throw you into. So that is where this additional probability comes from, right? So you may not exactly get the string that you want, but some string in some epsilon vicinity of this string, right? Which is not too far away, say in a Hamming distance sense from this string. Does that explain better? If I have to explain more, I'll have to get into more details, which is what I'm sort of trying to avoid here.
Ma'am, I'll ask more after the class.
Yeah, so maybe one thing I can tell you is this, that see the Fourier transform. So let's say that, so let me just note one thing. So remember that we said that the final state, let's say before you do the QFT dagger, okay? Basically what the phase estimation does is it starts your this is in the state ket u, right? Yeah. And what the data qubit is in is actually a state of the form. If you go back and, rewrite your Fourier transformed state in this way, then you can write this as j going from 0 to 2 to the t minus 1, e to the 2 pi I phi sub j ket j, right? 1 over 2 to the t by 2. And what the inverse Fourier transform is going to do is it's going to, you're doing it only on the data qubits, and this is going to take you to some state phi tilde ket u, right? So what the what this probability basically says is that you do the the inverse Fourier transform on this state, right? The actual final state that you have with the t qubits, right? And then you can expand this state after this inverse Fourier transform into a superposition of states around the actual state that you want. I don't know if that makes sense to you, but you can basically write down this Fourier transform, the inverse Fourier transform fully. Here I've just said an ideal case, right? This is the ideal case where it just gives you phi tilde, and phi tilde is maybe exactly phi or something. That's what I have written there. But in the non-ideal case, this is going to be some phi tilde which is in the vicinity of phi. Okay, so that is where this probability epsilon comes about. Okay, so maybe we move on, and then in the end we can discuss this a bit more if you wish. Okay. So just
yes, thank you.
Okay, so what is phase estimation useful for? It again seems a bit of a contrived problem. You're already given some unitary U, you're already given some eigenstate, some state which is prepared in an eigenstate. So what is the use of this? Well, it turns out that the use of this is in doing a very number theoretic problem called order finding. So let me see how far I can go with this today. And tomorrow we'll hopefully conclude by showing how this relates to factoring. But from here on, I must warn you that there's a fair bit of number theory that is involved. I'm again not going to, I'm going to try to avoid discussing too much number theory and show you only the parts which are essential. Okay, and for the rest, I will refer you to, of course, I'll refer you to Nielsen Chuang, which will then have further references. Okay, fine. So what is order finding? What is order? So suppose I have a pair of co-prime integers. So what are co-prime? What do you mean by two integers being co-prime?
GCD is 1.
Yeah, so they have no common factors. Other than 1, right? Okay, so let me say x and n, where x is understood to be less than n. Okay, now the idea of the order comes from the fact that you can define this modular arithmetic with respect to this capital N. So I don't know how many of you are familiar with the idea of modular arithmetic. This is basically your clock arithmetic, right? So yeah, so let's do a simple, so I don't know, do people know what, so when I say that A, suppose I say that A is B mod n, C mod n, then it means that A is such that it is b times n plus c. Does that make sense? Did I write that correctly? So it means basically that a minus c divides n, right? So when I divide one number with the other, I have what is called a residue, right? And this residue and this original divisor, when you equate, that is what defines a kind of closed arithmetic with respect to this number n. So
Ma'am,
for example,
shouldn't
we can.
be A and C exchanged?
Does it matter? So I can say a mod n is c.
Okay.
Yeah. I mean, it doesn't matter, right? It's basically that a is equal to c modulo n. That's what it means, right? So for example, I would say 2 is equal to 5 mod 3, which is equal to 11 mod 3, which is also equal to 8 mod 3. So if you want to write it the other way around, then you say that 8 is 2 mod 3. So the point is, this is the equality. 8 is 2 modulo 3, 2 is 5 modulo 3, or 11 is 8 modulo 3, etc. Right? So there is, of course, a unique set of numbers through which you will circle through, right? When you do this modular arithmetic. Now, what we want to do with this number x and this other much larger number capital N is we want to take powers of x. Okay? So when you take powers of x, okay, so I hope the idea of this modular arithmetic is clear. This is like your, for those of you who are really not familiar with this at all, this is like your clock arithmetic, right? So it's like 1 is the same as 13 modulo 12, right? 14 is the same as 2 modulo 12, etc. Right? Okay, so we now want to do powers of x modulo n, okay? And the order of this smaller number x modulo n is defined to be the smallest integer smallest positive integer r such that x to the r is 1 mod n. Okay, so we can do this simple exercise with, but remember that x and n are co-prime here. Otherwise, this definition really does not make much sense. So recall that x and n do not have any common factors. Okay, other than 1, of course. So first of all, why is this order r important, or why is the smallest positive integer important? Because you will notice that if x to the r is 1 mod n, it means x to the r minus 1 is 0 mod n. What does this mean? It means that x to the r minus 1 divides n, or x to the r minus 1, the factor of n. And note that x to the r minus 1 is itself x to the r by 2 plus 1 times x to the r by 2 minus 1. So one of these two must be factors, right? So this step becomes a crucial step in the factoring algorithm. Okay. So this is why order finding is important. This is also sometimes called period finding. There's a related idea of period finding. So we can just do a simple example to develop some intuition for this. So we can try to do this with, so let's say that x is 4 and n is 7. Okay. So what is 4 to the 0? So we can start doing powers, right? So we can put different powers for r. So we can start with r is 0, right? So 4 is what? It is simply 4 mod 7, right? Oops, I'm sorry. Start with r is 1. What is 4 squared?
2 mod 7.
Correct. For cube,
1 mod 7.
exactly. So now you'll start seeing that if you do 4 to the 4 and so on, this will actually cycle through these three numbers, 1, 2, and 4. Okay. So you can keep going, of course. So first of all, till what number do you have to check? So you've already found out the order, no? So the order of 4 modulo 7 is 3, right? That's the smallest power of 4, such that 4 to the r is 1 mod 7, right? So you've already found out the order. But so let's say that r goes from 1 to, is there a bound? Can one put an upper bound on this?
Phi of n.
What is phi of n?
I mean the like
Some totient function you're telling
yeah,
me.
totient function, yeah, Euler totient function.
No, it's just n. The totient function comes in when you do the factoring algorithm. Tomorrow we'll mention it, but yeah, so it turns out that, so we can show that this order must lie between 1 and n.
But ma'am, actually totient function will be lesser than n, right? So it's actually a stricter upper bound. No?
Yeah, probably you are right, but in general we can say that. So it's actually strictly less than n, you're right. So, but it's easier to argue that it should be less than n, right? Then not everybody may know the totient
Yes.
function, etc. Yeah. So how do we argue that it's less than n? So this is called totient function. I didn't mean to discuss this today. So who mentioned this? Would you like to define the totient function?
The number of numbers less than n which are co-prime with n.
So it's called phi. Actually, they write it like this, right? You can go look this up maybe. Okay, so well, it's easy to argue that this should be upper bounded by this n itself, and that is because if you start writing down these powers, x to the 1, x to the 2, etc., x to the n, there are n such numbers, right? This gives you n such positive integers. But if I look at this modular arithmetic, then the so in a modular arithmetic with respect to capital N, there are only these n minus 1 numbers. Actually, maybe I wanted to put x to the, yeah, so x to the 0 is of course just trivial. So let me not include the 0 here, right? The point I want to say is, okay, so let me include x to the n plus 1 here. Let me do this. Yeah. Okay, so let's say I go beyond n plus 1, right? So then there are n plus 1 such numbers here. And if I go from 0 to n minus 1, which is this is the set of numbers in the group, right? There's a kind of multiplicative group defined by the modular arithmetic with respect to n, right? So these numbers only circulate from 0 to n minus 1. So the point is, once I start going beyond n plus 1, then I must have powers which give me the same number here, right? So I must have then 2 powers such that x to the s is the same as x to the t modulo n, where both s and t are bounded by n plus 1. I think I'm making some mistake in this argument here, which I can just argue with respect to just n. Yeah, sorry, I don't want to include 0 here because 0 is just the number itself, right? So, okay, so let me do this, sorry. So there are n such numbers, and then there are n minus 1 numbers through which the modular arithmetic circulates you through. So there must be 2 powers within this, which give you the same number modulo n. Do you understand? When I take n powers, there are n numbers that I get, but the modular arithmetic only circles me through these n minus 1 numbers. So then there must be 2 powers which collide, and so this I can then take inverses again because x is co-prime with respect to n. So then it tells me that there must be an s minus t, which is 1 modulo n. So in fact, this is a kind of proof that first of all there exists an order, right? And this s minus t itself will actually be strictly less than n, right? And this is what we call the order R less than n. Okay, is this idea clear? All right, so I hope you have some handle on, yeah, was there a question?
No, ma'am.
Okay, so I hope the idea of the order is clear, and this example hopefully also showed you how to work out the order. And the motivation to do this, like I said, comes from the factoring algorithm and the fact that if you find the order, then you essentially have found one non-trivial factor, prime factor of n. Okay, so how does phase estimation make finding the order how does it make it easier than the classical case? So let me just state a few things now, and those of you who have seen assignment 4 will know that I have essentially made this order finding algorithm as part of the assignment, okay? Because there is nothing new beyond phase estimation except preparing the initial state. So let me note that classically, okay, first of all, what is the kind of resources you would need? So we need to, so the problem is to find R, the smallest R, of course. Such that x to the R is 1 mod n, right? And you're given x and n. So what sets the resource scaling for you in this case will be this capital N, which is the much larger number, right? So let us say that L is of the order of log n, right? Or that it is the closest integer function or the ceiling function or whatever, right? Which means that you need L bits to specify n. Right? Because 2 to the L is the closest integer to capital N. So you need L bits to specify n. Classically, there is no algorithm which scales as poly L, right? Which scales polynomially with L for order finding. So what we will do is, by using phase estimation in a clever way, it will turn out that there is a quantum way to do this, which does scale as a polynomial in L rather than scaling exponentially with L, right? So the key trick or the key step in the quantum algorithm for order finding is to define a unitary U. It always starts there, right? Such that, so let's say that you have some, let's say that you define this computational basis. So of course, if you need L bits to represent capital N, we are going to assume that there is a unitary that is acting on L qubits, right? Whose computational basis states are of the form 0, 1, etc. 2 to the L minus 1, right? So let me call this as, so let me just label this as ket y, right? Where y is basically some L bit string, right? The computational basis states are labeled by L bit strings. So this u, which is defined with respect to both x and n, does the following. It does xy mod n. So y is some number between 0 and 2 to the L, rather 0 and 2 to the L minus 1. So this xy is also going to be some such number, right? And what this unitary does is to do this. But how am I guaranteed that I can define such a thing after all? It's like I have some number theoretic operation which is basically saying x times y mod n, and I'm claiming that I can do a unitary which takes me from the state y to this state. So let's see this tomorrow, right? Let's look at this unitary a bit more closely. And that is as much detail as I will do for the, so obviously where does phase estimation come in? It will turn out that finding the order of x with respect to n will be like finding the phase of a particular eigenstate of this u. Okay, so we're going to map the phase, the order finding to phase estimation of a particular eigenvalue of this unitary u. And since phase estimation can be done efficiently, because the Fourier transform can be done efficiently, therefore order finding can be done efficiently. Okay, so let's continue tomorrow. Questions?
Ma'am, so that the previous question about the error or the
Yeah.
probability of failure.
Yeah.
So that probability of failure is like what happens when gates are not like physical, meaning the quantum.
No.
Fourier
It has
transform
nothing
is-
to do with the gates being inaccurate and so on. No. It doesn't have to do with that. That's
But
why I
when we
tried to explain it also, but I didn't have. Okay, so this is what I'm saying. So let's say that, so this is the point. So let's say that you're approximating phi with some phi tilde, first of all, right? There is an approximation that's involved here, right?
the QFT step itself, right?
Before that, see this phi, when I say that I'm using only t bits to represent phi, I may be truncating that representation, right? It may need many more bits. First of all, it could even be some irrational number, right? It could be some,
Right.
yeah. So there's no guarantee that within t bits I'm going to be able to truncate the representation of phi. So I'm first of all approximating it with some phi tilde, which has only t bits, which I'm representing with using only t bits. So this phi tilde is some number you can think of as between 0 to 2 to the t minus 1, right? And then this actual phi is such that if I do phi tilde by 2 to the t, then this difference is what you can call delta, and this delta is much smaller than 1. So this is the claim, right? Because this is some number, phi tilde is some number between 0 to 2 to the t minus 1. So the claim is that the next order of this, which is the, when you divide by 2 to the t, is very close to phi. So it's converging, it's very close to phi. Okay. Now you're doing the inverse Fourier transform essentially on phi tilde actually. Okay, so maybe I wrote this, yeah, maybe I shouldn't have written it like this. Okay, so let me write this as phi itself and say this is ideal. Okay, but this j bits that I have here, these t bits that I have here before the inverse Fourier transform, they are basically the t bits of phi tilde only, right?
Hmm.
So
Right, ma'am.
yeah, so I do the inverse Fourier transform on this phi tilde, okay, and that can represent as some superposition of all the basis states, the t basis states, right?
Hmm.
Then I can try to shift them by some, yeah, just give me a second. So the idea is that when I measure this final state, I'm going to get, I'm going to get something which is close to phi. And what is the probability that whatever I get is within some error, this kind of error bound of phi. That's what the probability is. Okay. So maybe I'll share some notes maybe on Moodle for this, and then you can see if that works out, right? Otherwise, tomorrow at the end, if I have time, I'll go over this again.
Okay. Yes, ma'am. Thank you.
Yeah, sure. Okay, so I'll see you all tomorrow then.